Hey, it's Dr. J. Moving on to 3.6 today. We are going to focus exclusively on one mother function, and that is the absolute value function today. So basically, we're just kind of taking this out of the family of all the other mother functions, and we're just going to specifically talk about all of the properties of the absolute value function, graphing it, finding intercepts and other types of behavior of the absolute value function. So this is, I could write it as y equals, or I could write it as f of x equals. It really means the same thing. And we're going to talk about the general form, also known as the vertex form. The vertex form is f of x equals a, absolute value of x minus h plus k. So this has already gone through the transformations. I might have mentioned in the last lecture a, formerly known as c. And I think I mentioned that I think I'm going to switch it to A, because as we move through the rest of the textbook, we often call the scalar A instead of C. It really doesn't matter. It performs the same task whether you call it A or C. Yeah, scalar. All right. And then we have H is the horizontal shift. Remember, it's reversed. So I'm not going to, I'm going to go through it, but I'm going to hope that we've already covered that. If this is a negative, then you'll go to the right. If this happens to be a positive, then you'll go to the left. In the vertex form, we typically write it as negative, even if it's positive, and I'll explain how that works in a minute. And then the K is the vertical shift. The vertical shift, it'd be cool if we used the letter V for vertical. We do use H for horizontal, but we use K typically for vertical. All right. And so let me explain how this works. If you have an absolute value function that's already gone through the transformation, there is a quick way to find the vertex. It's just H and K. It's just H and K. So that's why we call this the vertex form. All right. If A is greater than 0, that's the scalar, A, then the absolute value looks like this, and HK is the lowest point. So the vertex is the lowest point, sort of the bottom of the letter V. So this is what the shape would look like. And if A is less than 0, then it's upside down. Like this. This is still HK, H comma K, but it's the highest point. All right. If there's no A, if you don't see an A, that just means it's 1, and that would fall into this category, greater than 0, if you don't see an A. That'd be an invisible 1. We'll do an example in a minute. Okay, so let's go ahead and get after it. This is the vertex form. I'm going to need to erase this, so maybe I will write it up here. I'm going to hold off on doing the graphs right now, and we're just going to talk about the critical values or the important values on the graph. So my first example will be just to find the vertex. I don't know why I'm thinking so hard. Okay. So let's go ahead and go through all of these. I will mention that f of x is just a general name for function. Sometimes we call it f, sometimes we call it y, sometimes we call it g. These are all different ways of representing the name of the function. So they all mean the same thing. I think at this point in the semester, I don't really need to say that. These are all y values, just different ways of saying y. In these problems, I'm only looking for the vertex, so all I care about is h and k. You do want to have this be a negative. So if this is a negative already, then your h is the opposite of -3. So h would be 3. And then k is exactly what it looks like. K is 5. So in this example, or in this piece of the example, the vertex is 3, 5. And it's really cool in this section. This is one of the only functions. There is one other function that we'll talk about in a future chapter from the family. But today, this is really the only one of the functions that we've discussed in which you can just snap out the vertex very quickly like that. You don't have to run through all of the table of values and all that jazz. You get it very, very quickly. All right. This is an absolute value. Be careful you don't make it look like a 1. So I always try to make my absolute values look taller than their surrounding numbers. All right. And then this is what I was mentioning about the invisible a. If you do not see a scalar, it's like an invisible 1. You know, like this. Invisible 1. I rarely ever write it. I'm only going to write it this one time just to show you that even if you don't see an A, there's definitely an A. Now, in this particular problem, the A value doesn't really matter, right? The A value is just the scalar that doesn't contribute to the vertex. So the vertex is the opposite. So this is technically x minus -4. That's another way of saying x plus 4. And so that means that h is -4. You can just do this step mentally. I mean, if you want to write it in your notes, I highly recommend it one time. Write it in your notes once. And then for the rest of the semester, you'll just do it mentally. If that's positive, you can just jump over here and say h is -4. And then k, there's no opposites for k. K is just whatever it is. So k is -6. I was looking up here and almost wrote 5. So the vertex would be -4, -6. When I actually get deeper into the lecture, I will just read the equation and bam, write down the vertex. So I'm only going to show these steps one time. Okay, here is your A. Your A is 3. You can ignore that. You need to know what to ignore. We're only looking for H and K. H is 7. It's not -7, it's 7, right? Because in the formula, the negative is already there, and so we take the opposite of the H value. So the opposite of -H is H. So the opposite of -7 is 7, all right? And then if there's no K, it's an invisible 0. There are 2 types of invisible numbers in mathematics. You probably learned this when you were a little kid. 1 is an invisible number. You can't see a 1 when it lies in front of an expression. And a 0 is the other invisible number. So if it's a scalar, an A, and it's invisible, it's a 1. If it's a shift, horizontal or vertical, then that means it's a 0. So our K is going to be equal to 0. So our vertex is 7, 0. All right. I don't have room for one more part. I'm going to put it up here. This will be our part D. Okay, so I'm just continuing the same problem. Find the vertex. So your A is -5. Ignore that. Yeah. There's no H. Yeah, it's invisible, so that means H is equal to 0. Just like over here, if there's no K, if you don't see a K, well then that means the K is equal to 0. If you don't see an H, you don't see any horizontal shifting, that means it's 0. And then your K is 2. So for this function, y equals -5, absolute value of x plus 2, the vertex is 0, 2. Okay. Before I erase all of this, I just want to point something out. In a minute, we're going to graph these types of equations, and I want you to know if the scalar is negative, then that means it's an upside down V. So you can kind of run down these. This one's going to look like an upside down V with a vertex. So we're basically just getting one dot, and then we know which direction it points. This one's also going to be an upside down V. So it's good to have an idea in your head of what's going on. This one would be a right side up V. Yeah, because the scalar is 1. And this one would also be a right side up absolute value. So that, just keep that in mind, because you know at some point we're going to break out the graphing board and do some graphing. Okay. So after we find the vertex, the next thing we want to do is find the intercepts. Intercepts are where the graph crosses one or more axes. So these are called X intercepts. And I just made that one up. I mean, obviously that's not, I don't have an equation yet, but we'll have one in a minute. And then this one over here is called the Y-intercept. Okay. The Y-intercept always exists. Just plug in x equals 0, or in other words, f of 0, and solve for y. Well, you're actually not solving, you're evaluating to get y. All right. And then you're going to write it as an ordered pair. Zero comma y, whatever that happens to be. Or 0 comma f of 0. This is a nice functional way to write it, because remember, f of 0 is just going to give you the y value. Okay, let's do that first. Let's find the y-intercept. That'll be very easy because it always exists. All right, so I'll give you a function, and I'll ask you to find the y-intercept. Okay. You can write this as f of x, or you can write it as y. But make sure that you plug 0 in for x. So make sure your x value is 0. The absolute value of 3 is just 3. And so your y-intercept is 0, negative 2. That's your answer. You do have to write it in the correct order. If you accidentally write negative 2 and then 0, you're going to get it wrong. All right. A y-intercept always has a 0 in the first spot. Don't look at the picture, because the picture doesn't match my answer, because I just made this picture up. The actual picture would look more like this. Actually, no. I don't know why I'm wasting your time with this, but it would actually look like this. That's better. So this is a negative 3 and 4. See the vertex? The opposite of positive 3 is negative 3 and positive 4. So this is going to make graphing so much easier than it was in the previous section, which means I can probably get through this much more expeditiously. Faster. All right. So that's the y-intercept. The y-intercept is basically a free answer. Come on. I mean, the only mistake you might make is you might make some kind of a negative sign error or something like that. But other than that, typically I give away this answer. Yeah? I hope you get it on the test or quiz or whatever, because it's free. All right. The x-intercepts are not free. So that's why I emphasize the y-intercept is the free answer. The x-intercepts, there are 3 possibilities. One, you could have an absolute value that has none. That would be DNE, does not exist. So you would literally just type DNE. That means none or does not exist. That could happen, yeah. It can actually happen in 2 different ways. It could happen like that, or it could happen like this. Either way. These are both does not exist because the graph is never touching the x-axis. We hope that doesn't happen, but we have to keep that in mind that that could happen. There could be some DNEs. There could be one x-intercept. Something like that, or possibly the other way. Yeah. These are basically considered the same possibility. That you have one x-intercept. We call that x1. Yeah. x1. I know this is going to look like more than 3 possibilities, but I'm counting this as one possibility. I'm counting this as another possibility. I mean, if you really want to count every single possibility, it's going to be a lot more than 3. So just we're kind of grouping them together. And then the more likely thing is that there could be 2 x-intercepts. So you would write them as x1, comma 0 and x2, comma 0. So you have 2 distinct x-intercepts. And again, this could be upside down. All of these possibilities have the alternate possibility that it could be upside down. And then if you really wanted to get crazy with it, you actually have other possibilities in the other quadrants as well. We're not going to go there. So basically, there are 3 possibilities. You either have no x-intercepts, you get 1 x-intercept, or you get 2 x-intercepts. Okay. To find the x-intercepts, you're going to set y equal to 0. So example 3, f of x is the absolute value of x minus 4 minus 2. So when you're finding an x-intercept, you want to set y equal to 0. But sometimes there is no y. So I recommend rewriting it, unless it's already rewritten. Sometimes I give you problems where it's already written in the form y equals. But sometimes I give it to you in f of x form, or maybe g of x form, or something like that. And then plug 0 in for y. Be careful, don't put 0 in for x. You don't want to do that. That would give you the other answer, the y-intercept. This is the x-intercepts. Okay. I like to reverse it like this. And we're going to add 2 to both sides. And now we're going to review chapter 2, section 7, I think it was. You're going to split this up. All right. One of them is x minus 4 equals negative 2. I'm just going to put a comma. The other one is x minus 4 equals positive 2. Remove the bars. That's what we call these things. We call these the bars, or the absolute value bars. You can just call them bars for short. Make sure you don't accidentally change that 4 into a positive 4. All right, that's like an unresolved childhood issue. When you were in 5th or 6th grade, you probably learned, oh, take an absolute value, just take the negatives and turn them positive. And that's not the way it works, right? You remember we talked about this back in chapter 2. You don't change the inside, you actually change the outside value. And then you move the inside value, the 4 moves over to the other side. So this is your x1, and this is your x2. Subscripts are not required, but since I've already used them, I'm going to go ahead and keep them. The subscripts are not necessary. Why did I use them? Well, because when I defined the 2 different answers, I want to separate them. This is the first x. That's how you read it, actually. You don't read this as x to the 1. You read this as the first x, and then you read this as the second x. A subscript is really just an indicator or an index of when did you show up. Did you show up first? Well, then you're 1. Did you show up second? Well, then you're 2. It doesn't mean anything other than who came first. And it's a little bit like the chicken and the egg. It really doesn't matter. If the chicken came first, well, then there was an egg. And if the egg came first, well, then there must have been a chicken. And so it's a sort of infinite loop. And I don't really need to get all philosophical with it. All right, here's what I want to make sure you do. Give me 2 separate answers. Don't try to put these 2 answers together. Give me 2 separate answers. So the answers are 2, 0 and 6, 0. All right, make sure that the 0 is in the second position, the y position, and make sure that you don't put the 2 and the 6 together. I often get students that will solve the problem correctly. They'll get the answers 2 and 6, and then they'll type in 2, 6. Oh, and I'm like, why? Why'd you do that? You had it right. But it's not 2, 6. It's 2, 0, 6, 0. And it really does matter. I'm going to be picky about that. No partial credit, right? You got to be right. Okay. So this is the case where you get 2 X-intercepts. Okay. Well, here's an example. Find the X-intercepts. Example 4. This one I've already written in the Y form. So just go ahead and take it. Set y equal to 0. If you've got any scalars on the outside, you want to divide by the scalar to get rid of that scalar. Okay. And then what? Well, this is equal to 0. So if the absolute value is equal to 0, you can just remove and set it equal to 0. There's only going to be one solution. So you're not going to say positive 0 and negative 0. That wouldn't make any sense, right? There aren't 2 zeros on the number line. There's only 1 0. So you can just remove the bars and set it equal to 0. And your solution is 5. So this only has one x-intercept. It has another fancy name that we'll learn in chapter 5. It's called the zero of the function, if you want to start learning the lingo now. It's just a fancy way to say the x-intercept, the zero of the function. In other words, the y value is 0. So even though I say find the x-intercepts, there might not be 2 of them. In this case, there's only 1. All right, let's try another one. Might as well. I want to show you all the possibilities. You never know what you're going to get, so you have to be prepared for all of the possible outcomes. So find the x-intercepts. All right, find the x-intercepts. So again, g of x is really y. Yeah. And we're setting y equal to 0. I would just memorize that. If you want to find the y, you set x to 0. If you want to find the x, you set y to 0. It's always backwards. Whatever you're looking for, you want to make the other variable 0. All right. I like to do this. I like to put my 0 on the right-hand side. It just saves me one line of work because I've already got it set up like this. So now remember, you want to move all of the constants onto the right-hand side. I mean, if you're doing it this order. If you're doing it the other order, move them to the left-hand side. Okay, that moves the 8. And now you want to move the scalar. The scalar is 2. All right, and now you want to read this carefully. Don't just drive right through the house, right? Don't just drive right into the garage door. You know, you got to look. Stop. The door's closed, right? You cannot go any further. The door is closed, right? How could the absolute value be equal to -4? That can never happen. It's impossible, right? Remember what absolute value is. It's an always positive function, right? Remember the mother function? Yeah, there's your mother function for absolute value. It's always above 0. So how can it possibly be equal to -4, right? -4 is way down here. This function never equals -4. Never mind the +3. The +3 is meaningless. It's not going to change the value. So stop. There's no solution. That means there's no x-intercepts. So the answer is DNE. They do not exist. Okay. All right, well, now we're going to start graphing. If you want to use the techniques from 3.5, the transformation of function technique, I think I showed one example of it, of the absolute value back in 3.5. Feel free to review that, or if that technique was working for you, you don't have to reinvent the wheel here. You can just continue to do it that way. I'm going to show you a slightly different technique. This technique involves no transformations, just finding the vertex. All right. So look at the inside. The inside, there's no horizontal shift, so that's 0. And then look at the outside. That's your vertical shift. That's -3. And I know immediately, without doing any real calculation, I'm not making a table. I'm kind of freestyling it here, but I'm freestyling it, but I'm following a pattern. So I don't know if you can really call that freestyle. 0, -3, I automatically know my vertex is right there. So you're going to plot this point first. All right. Then find the Y-intercept. That should be pretty easy, right? Just plug in 0. Oh, no, look what happened. It's the same as the vertex. Look, the vertex and the Y-intercept are coincidentally the same. That will not always be the case. So that's why I'm showing you how to do it, in case they don't come out to be the same. All right. Next, find the X intercepts, if there are 2 of them. So take this equation and set it equal to 0. Notice I'm moving the y onto the right-hand side, just so it doesn't look backwards. And then I got +3, +3. Absolute value is equal to 3. Stop and think. Is that possible? Sure, it's possible. The absolute value could be equal to 3. In fact, there are 2 answers. One of them is 3. The other one is -3. So you've got 1, 2, 3. 1, 2, -3. Y is also -3. Connect the dots, and you're done. Right? I'm not writing these as ordered pairs, but you could if you really wanted to, or if you were instructed to. So if instructed, you should write this as 3, 0 and -3, 0, because they are 2 separate points. All right, there you go. There's your graph. I'll ask about domain and range later. Let's get a few of these under our belt first before we do that. All right, another example. So graph y equals absolute value x plus 4. So go ahead and find the vertex. All right, this time there is a horizontal shift. It's +4. Remember, horizontal is opposite, so +4 actually means -4. It's been shifted to the left. It doesn't look like there's a vertical shift, so that means it's 0. If there is no vertical shift, that means that there is none. None is 0. There's your vertex. Let's do the Y-intercept. All right, I might need to do a little bit of math here. Y equals 0 plus 4. You could probably just do that in your head. 0 plus 4 is 4. Absolute value of 4 is 4. All right. Notice it's not the same as the vertex. All right. And then the X intercepts, I always say intercepts, even if there are none. I'll still say intercepts. And even if there's only one, I'm not going to say intercept. I'm going to say intercepts, but there could possibly only be one. All right, so how do we do the x-intercepts? We go back to the original equation, and you set y equal to 0. And if you've been following along, I like to put my 0 on the right-hand side. It just looks a little cleaner. Oh, look, 0. There's only one 0. So there's only one solution because it's 0. If it was equal to 5 or 6 or 12, there'd be 2 solutions. But if it's equal to 0, there's only one solution. Move the 4 over. Oh, what do you know? That's the same as the vertex. Okay, if you would have noticed that sooner, right? Hindsight is, 20/20, as they say, the old cliche. Now looking back on it, I kind of feel like, oh, wow, why did I do that? I should have just noticed that that was like that, and I wouldn't have to do all the extra work. Right? If you make an observation early in the process, you can save yourself a little bit of suffering. Okay. Let's go ahead and graph this sucker. So we got the vertex. You want to plot that first. I'm labeling them just to be neat about it. You obviously could just say -4 there. That's what it will look like on the graph. But I'm just trying to be extra neat. And then 0, 4. Now here's where you have to remember the shape. You got to remember what is the shape of this mother function. This mother function has a very, very particular shape that only this type of function has. It's not a straight line. It's a V vertex. So at the vertex, it has to make the shape of a V. And it has to have the same slope but opposite value. So if this slope is 1, then this slope is -1. Just do a mirror image onto the other side. And so that is your graph. Not too bad, huh? A lot easier. A lot easier than making a table and doing all these transformations and then, shuffling around all the numbers and things. This is just going straight to the point and boom, you get the graph. I really wish that we had a technique like this for some of the other functions. Maybe we will develop one over time. Maybe this will catch on. We'll go, hey, wait a minute. That's a much more effective way to do it, right? A 4, it's a 6. Okay. So f of x equals negative. Now this is weird because that looks like a 1, but that's an absolute value. This is actually an invisible -1. Although it's not totally invisible. You can see the negative, you just can't see the 1. So that's your scalar. Right? It tells us that the graph goes like this. Yeah, it looks like this. So if I don't get a graph that looks like that, I know I did something wrong. So just keep that in the back of your mind. You're actually not going to use it too much until you're actually breaking out the graph board or your mouse, and then I'll show you what that means, okay? Let's first just find the vertex. You could do that just by looking. So the opposite of -2 is 2. and exactly 6, so the vertex is 2, 6. Let's do the Y-intercept. Very, very standard set of steps. Plug in 0 for x. Like that. All right. If you want, you can just call this y. Be careful when you see 2 negative signs. You probably learned many years ago that 2 negatives make a positive, and that's just not always true. In fact, that saying never should have become a saying. The proper saying is 2 negatives make a positive sometimes, but sometimes 2 negatives make a negative. Yeah, so this is actually one of those cases where 2 negatives make a negative. Yeah. It's because it's an absolute value. You're taking the absolute value of a negative, which is a positive, and then you're turning that back to a negative. So the 2 negatives eventually turn into a negative. Then bring down the plus 6, and your y-intercept is 0, 4. All right, make sure you put it in the right order, 0, 4. All right, let's find the x-intercepts. Okay, so the x-intercepts, take this equation and set it equal to 0. Again, this is like the y value. F of x is the y value. I often recommend just wiping out f and just calling it y right when you get the problem. All right, erase it, replace it with y. Okay, let's go ahead and solve this thing. Remember, there are 3 possibilities. I can either get 1 solution, 2 solutions, or no solution. Let's see. It all depends on the right-hand side. So you got negative on both sides, so you're going to divide by -1. Okay. Now let me tell you a little trick. If you get to this step, at this step, so the step where the absolute value has been isolated, you haven't yet taken out what's on the inside yet. So you got to stop, take a breath, and then look at the possibilities. If this is a positive number, there are 2 solutions. If this is a negative number, there is no solution. All right. So positive means 2 solutions. Negative means no solution. And if this is 0, 1 solution. All right. This is just a mental stop sign. So mentally stop. That's supposed to be a stop sign. I don't know if that looks, there we go. That looks a little bit better. So at this point, stop, look, and decide how many answers am I going to get? Am I going to get none? Well, if that's a negative, I would get none. Well, I'm not going to get none because that's not negative. If that's a 0, then I'm going to get 1 solution. If it's positive, I'm going to get 2 solutions. So we're at the positive possibility, so we're going to get 2 solutions. So one of them is equal to -6. The other one is equal to +6. Those are the 2 solutions. Notice that I remove the absolute value bars. If you still have the absolute value bars on right here, you're going to get the wrong answer. All right, you got to remove those bars. Now you're going to add 2 to both sides. So this is your x1, and then you're going to add 2 to this side, and that's your x2. And again, the subscripts are not necessary. You can just write them like this. Subscripts are really just an organizational tool to help you and me and other people keep track of all the different solutions. If you just call them both X, that's fine. Yeah, as long as you know that they're not the same value. That's one of the problems with variables, is if they look the same, your brain might think that they're the same. But that's why we use subscripts to say, oh no, you're not the same as that one. You've got a slightly different index, right? My battery's about to die. There we go. All right. We're supposed to be graphing this thing, right? So we've got the vertex, we've got the Y-intercept, and we've got the X intercepts. All right, let's give it a go. All right, here, let me write this one here so I can cover this up. That's our Y-intercept. Oh, coincidence. I didn't plan that, but that's kind of convenient. 0, 4, I'm just reusing it from the last problem. Sometimes two completely different problems have the same solution, or at least the same Y-intercept. All right. Oh, I blew it, though. I blew it. You're supposed to plot this one first. It doesn't really matter on paper. You can get away with it. But on the computer, you won't get away with it. So you got to do the vertex first. So what's that? 2 and 6. So right there. Okay, so that's my vertex. That's my Y-intercept. Then I got my X-intercept, -4, 4, 6, 2. And then what was the other one? 8. So 1, 2, 3, 4, 5, 6, 7, 8. And this is an upside down V. And there you go. That's your absolute value graph. I said we would talk about the domain and range. I mean, I'm basically done with the problem, but I just want to give you the answer for the domain and range in case I ask. So just really quickly before I erase it, domain is a free answer. Take it for the whole chapter. Not the chapter, the whole section, excuse me, 3.6. All of the questions in 3.6, if I ask you for the domain, they all have the same answer, -infinity to infinity. You can have it for free. The range, though, is not going to be free. You have to look very carefully at the graph and look at the Y values. The Y values are pointing down to -infinity, so put that first. And they go all the way up to 6 and a close bracket at 6. All right, let's try another one. Let's try another one. Example 9. Okay, example 9. What was my suggestion? Immediately get rid of the F and just call it Y. Just not a bad idea. First thing you want to do is find the vertex. You look only at the inside and the outside. Don't look at the scalar for the vertex. So opposite of -6 is 6, and then the vertical is exactly -5. So there's your vertex. The Y-intercept, you're going to plug in 0. Okay. So you've got the absolute value of -6. That's just going to be 6. You can remove the bars, or you can use a dot. Doesn't matter. These mean the same thing. But you do have to remove the bars. Otherwise, you're going to get the wrong value. That's going to be 12 minus 5. So that looks like 7. So you get 0, 7. That's your Y-intercept. All right. Seems pretty typical, right? X intercepts. Set this thing equal to 0. I like to put it on the right. Add 5. Divide by 2. You can write this as a decimal if you like, 2.5. Or you can just leave it as 5/2. I do want you to know that that's 2.5 though. So however you write it, I hope you know that that's 2.5. And now stop and think. How many solutions are you going to get? Well, that's not negative. So I know I'm going to get at least 1. It's not 0. So I know I'm going to get 2. Yeah, because that number is non-zero and non-negative. So that means I'm going to get 2 solutions. I don't know what they are yet, but I know I'm going to get 2 of them, whatever they are. Come back up here, remove the bars. One of them equals -2.5, and the other one equals +2.5. Add 6 to both sides. You're going to get x is -3.5. Yeah, -2.5 plus 6 is -3.5. And then the other one would be 8.5. Okay. What's the problem with these? Well, they're not that bad. Right? They don't have a major problem. But they do have a small problem, and that's that they're decimals. You may not be able to plot decimals. It just depends. Some graphs allow decimals. Some don't. If the graph does not allow decimals, then you're going to skip it and use the scalar instead. Instead of the x-intercepts. I mean, it's not as if they're not going to exist. I mean, these definitely do exist. But look how they look. It's -3.5, 0, and then the other one is 8.5, 0. They exist, but they're not really nice numbers. I mean, you could give it a try. I encourage you to experiment. I sometimes do that. I'll open up one of your problems and I'll say, oh, let me see if I can plot 2.5. You know, some of the problems allow it and some of them don't. All right. So, you know, just there it is. You know, if you get a whole number or an integer, then you can definitely plot it. All of the graphs allow integers, but they don't always allow decimals. It's just it's a hit and miss. You know, it just depends on the programming. So what we're going to do is we're going to use the scalar, the 2, instead of the x-intercepts. And the x-intercepts will still exist, I'm just not going to actually click on them. Okay. So let's see. So do the vertex first. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, -5. That one first. Okay. And then I got my Y-intercept. My Y-intercept is 0, 7. 1, 2, 3, 4, 5. Oh no, sorry. I should have planned that one out a little better. Redo. Start that over again. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, -5. There's my vertex. And then there's 0, 7. 1, 2, 3, 4, 5, 6, 7. So right here. Okay. But I don't have the X intercepts, right? I mean, I know where they are. One of them's like right about here, kind of in between 3 and 4. And then the other one's kind of over here at 8.5. But I might not be, I don't want to rely on that. So instead, you can use the scalar sort of like slope from chapter 2. So 2 is equal to 2 over 1. So you're going to go up 2, and then you're going to go left and right, because it's an absolute value. With a linear function, you go left or right, depending on which direction the slope is going, right? But this is a V shape. The slope is going to go in both directions. So it's going to go up 2, and then it's going to go both left and right 1 unit. So I'm going to go up 2 units, and then I'm going to go left 1 and right 1, and that's going to give me my slope. Okay, and then you might just, in hindsight, after you've done it, look. Just look for fun. This is 3.5. Somebody almost got extra credit. So close, look. I'm so glad I drew the graph. That's 3.5, right? It's in between 3 and 4. I wrote -3.5. Sorry, kids. I saved my own problem. I found my own mistake, so no extra credit. But it was close. You almost got it. Some of you are probably already typing the email, right? And going to go, oh, no, he found it. So I'm glad I fixed that. Look, sometimes the graph really kind of tells you whether or not you made a mistake or not. And then you might look here and see if that's 8.5. That is 8.5. Look, that's 6. That's 7. That's 8. That's 9. And it's right in between 8 and 9. That's 8.5. There you go. All right, so I didn't actually click on those points. I clicked instead on these points. You don't have to click on all of them. I think you've hopefully figured this out in the other graphing sections. You're going to do the vertex plus 1 additional point. But on paper, you need to do more than 1. All right, so I recommend doing a bunch on paper, at least 3 on paper. And then when you go to the computer to click it in, just pick the one that you like best. I'm also going to ask for domain and range. Domain is, of course, a free answer. Range is not free. Look very carefully at the y values. The y values go from -5 all the way to infinity. So your range is from -5 to infinity. Okay. We'll try another one? Try another one? Yeah, I know you do. How about if I call it the last one? Yay, it's the last one. All right, last example. Last example. All right. Oh, that's not supposed to be 18. It's supposed to be 8. I don't know why I wrote 18. I think my brain saw the absolute value bar and thought it was a 1. My brain, I have a brain too, yeah? All right. Okay, so vertex, that's kind of a free answer, right? I mean, it's cheap. It's not necessarily free, but it's cheap. You just look at the equation, take your answer. So the opposite of -4, opposite of +4 is -4, and then exactly -8. So there's your vertex. Your y-intercept. You getting pretty good at this by now? You want to try it with mental math? Let's do it with mental math. Don't you love mental math? This is how I expect you to do it as you mature through the course. Plug in 0, you get 4. Absolute value, you still get 4. Multiply by -3, you get -12. Subtract 8, you get -20. Ah, caution. It may not fit on the graph. I rarely ever have a graph board or a graph window that goes all the way to 20. It's just, if I do that, I've tried it before, it makes it so small that you really can't see it. You have to blow it up to the size of the whole screen to be able to see that. So typically my graphing boards usually end at around 10, typically, plus or minus 10. Sometimes I go a little smaller, 5, 6, or 7, depending on the problem. But I rarely ever go to 20 unless it's a special circumstance. So we might not be able to plot that point. Okay. Let's do the X intercepts. I'm not going to try this with mental math. You can do the Y-intercept with mental math. You might be able to do the X intercepts with mental math, but I don't know. That's a stretch, right? It's a much more sophisticated procedure, right? So you have to actually write down every step. So now move the 8 to the other side. Divide by -3. Get rid of the scalar. Stop and think. Remember the rule. If this is negative, there's no solution. There are no x-intercepts. So we're in a real bind, aren't we? Our y-intercept probably won't fit on my graph board, unless I really make a giant graphing Cartesian system, as we call it. So I'm probably not going to be able to do that. I'm definitely not going to be able to plot the x-intercepts because they don't exist. So I only have 1 point. If this happens, you need to use the slope, the scalar, as the slope. So negative 3 over 1. Remember, there's an invisible 1 underneath that. So you're going to go down 3, and then you're going to go both left and right 1 unit. All right. Put the negative with the 3. Don't put the negative with the 1. So if the scalar is negative, associate it as going down. If the scalar is positive, then think of it as going up. So I've got my graphing board here. Vertex, 1, 2, 3, negative 4, 1, 2, 3, 4, 5, 6, 7, negative 8. So there's my vertex. Notice the Y-intercept. Zero, negative 20. Definitely doesn't fit on the graph. All right. Even if you click the zoom button is just going to blow it up larger, and it's still not going to fit. So there's your vertex, and now you're going to do the slope. Oh, shoot. Sorry about that. I'm going to put my x-axis way up here. Sorry about that. 1, 2, 3, 4, 5, 6, 7, 8. The whole graph lives way down here below negative 8. So now I'm going to use the scalar kind of like a slope. So starting at this point, I'm going to go down 3 units. So down 3 units. 1, 2, 3 from negative 8. And then I'm going to go both left and right 1 unit from that central, what we call the axis of symmetry. And there you go. The red lines won't actually exist, so this is what your graph will ultimately look like. All right, and now you can see why DNE does not exist, because the graph lies below the x-axis. It never actually touches the x-axis. You can kind of see where the negative 20 would be also. If the graphing board were bigger, you know, and I go 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, negative 20, you could kind of use your imagination and see, oh, look, if we had a big enough paper. Sorry about that. The phone's ringing. It doesn't matter. We're pretty much done. I'm just closing up shop here anyway. If the graphing plane is larger. So if you do have a big enough graphing plane, you certainly could have graphed the whole thing here like this. Before I dismiss, let me just do the domain and the range. Domain, free answer, negative infinity to infinity. Look, that's the x-axis. Range, it's going down. That's negative infinity, and it stops at negative 8. All right, we're not done. This is just a break. I'll come back with another video, part 2, 3.6. So until we meet again, this is Dr. Jordan. I'll see you on the internet.